All right, 5.1 was the mid-segment theorem. So we learned what a mid-segment was, which is the segment connecting the midpoints of two sides of the triangle. And then we learned the mid-segment theorem, which said that the mid-segment is parallel to the third side and half its length. So for the warm-up numbers 1 through 4, you're using the figure there at the right. The first one says if UV is 13, so if this is 13, find RT, which is what? 26. We're going to double it, right? So if you got the mid-segment, you're going to double it to get the side. If you got the side, you're going to cut it in half to get the mid-segment. So then the next one, ST, which is this whole side, is 20. UV would be what? Or UW, sorry, would be 10. Good, half of it. Then said, if the perimeter of triangle RST is 68 inches, find the perimeter of UVW. RST is the big one. UVW is the little one. What's the perimeter? 34. How do you know that? Good. Every side length is half, right? So number 4 says if VW is 2x minus 4, so 2x minus 4, and RS is 3x minus 3, what's VW? So what's the relationship between these two? Okay, I could either say that 2x minus 4 is 1/2 of 3x minus 3, or I could say 2 times 2x minus 4, which is a lot easier. Good. So then from here, I can say 4x minus 8 equals 3x minus 3. Subtract the 3x. X minus 8 equals negative 3. Add the 8. And x equals 5. Is that what it's asking for?
No.
Nope, it wants VW. So I got to do what? Good. Take the 5 and plug it back in. 2 times 5 minus 4. Raise your hand if you got all 4 right.
No, I got the last one.
Good. Okay, but do you know why now? Okay. All right, this one says place a rectangle in a coordinate plane so that its vertical side has a length of 2x and its horizontal side has a length of 6x. Label the coordinates of each vertex. So this is a lot like the example that we did last week. I'm going to pull in a coordinate grid. I'm going to start with any length of vertical side. So let's say I go from 0 to 4, okay? If this is 2x and my length is 4, what is x in my scenario? 2, right? So my horizontal side is 3 times that length, right? Or 3 times 4, which would go all the way to 12. That's my 6x. Now it says, so let me make this. It doesn't matter how long you make your individual sides as long as the proportion is still the same. The vertical should be 1/3 the length of the horizontal. So now when it says label the coordinates of each vertex, first of all I have to complete this this rectangle. So this would be 0, 0. This would be 6x, 0, because I went to the right 6x, but I didn't go up or down at all. This would be 6x, 2x. And this would be 0, 2x. So you don't want exact coordinate points there because everybody should be the same. They're all in relationship to the side lengths. Questions on that one?
Wait, so how did you get your 6x now?
You
just said put it in.
I just know no matter whose drawing you're looking at, you should have the same coordinates, right? Maybe they're different sizes, but from left to right on that bottom one, it went from 0 to 6x.
Yeah.
And then from bottom to top, it went up 2x. And then where they meet is that 6x, 2x, because I went to the right 6x and I went to up 2x.
So let's say you had, instead of you did 4, you do 6, so would be 3, and then you would go 3 times 6, 18 for your 6.
So if you went up to 3, is that what you're saying? Yeah.
Alright.
Okay, let's look at the 5.2 is called using perpendicular bisectors. So we're going to learn what it is, and then there's a couple of properties about it that we're going to learn to apply. So by definition, a perpendicular bisector is a segment, ray, line, or plane that's perpendicular to a segment at its midpoint. So it has to hit at the midpoint, and it has to be perpendicular to where it hits. So in this diagram, CP, either line, ray, segment, is the perpendicular bisector. to AB. So you can't bisect a line, right? You can only bisect a segment. You can't bisect a ray or a line. And I know this because P is the midpoint of that segment and the right angle. So you have to have both parts. Think about the word. It says perpendicular, that's the right angle. Bisector, that's it, cuts it in half. The perpendicular bisector theorem, so it has a name, you don't have to write it all the way out, says in a plane, if a point lies on the perpendicular bisector of a segment, then the point is equidistant from the endpoints of the segment. And equidistant means same distance. After we're done with this one.
So if you find the distance from one endpoint, then it's the same as the other.
Correct. So on this one, you still have the same perpendicular bisector, right? CP is still the perpendicular bisector, which means any point on CP, which in this case they show C, is equidistant from the endpoints of AB. So these two are going to be congruent. If I put a point down here, let's call this E, then E to B would also be the same as E to A. They're going to be equidistant from the endpoints. Think about why that's happening. What shape are we making with those? Triangles. What's true about the top two triangles, the one with the blue? Without this.
Equal and no, they're
Are the top two is this one congruent to this one? Why? Side angle side, yes? They have the reflexive side, they have the right angles that would be congruent, and they have the bottom side. So if they're congruent, what's true about all their parts? They would be the same, and that's what? Good. Okay, so no matter which one I pick, I always have the side that's the midpoint, that's in two parts. I always have the reflexive side, and then I've got the right angle. So this just makes it a lot shorter, okay? Perpendicular bisector theorem. Okay, converse to the perpendicular bisector theorem. Says the opposite, right? If in a plane, if a point is equidistant from the endpoints of a segment, then it's on the perpendicular bisector of the segment. So this time it's saying if I already know that these are congruent to this, then I can say that D lies on the perpendicular bisector of AB. So this is the converse, which the if and the then, this time we know it's congruent, it's equidistant, so then I can state that it's on the perpendicular bisector. Okay, concurrent lines, another term. Concurrent lines are three or more lines, rays, or segments that intersect at the same point. And the point of concurrency is the point of intersection of the concurrent lines, rays, or segments. So if I have three lines that intersect in the same point, these are concurrent lines. And this point, let's say this is just point A is the point of concurrency. Theorem 5.4, which again, remember, the number is no bearing, right? It just means that it's the fourth theorem mentioned in the 5th chapter, okay? Is called the concurrency of the perpendicular bisectors of a triangle. So if I have all three perpendicular bisectors drawn in my triangle, then they would all meet at the same point. The perpendicular bisectors of a triangle intersect at a point that's equidistant from the vertices of the triangle. So not only do they meet, but that point is equidistant from the vertices of the triangle. So if you look at this diagram, first of all, how do you know which ones are the perpendicular bisectors?
Because of the equal distance.
They should be marked, so there's lots of stuff missing from this diagram. They should be marked equidistant, so this looks like it is the midpoint, right? But this should be marked like that, this to this, and this to this. If that's marked, then at least I know it's at the midpoints of all of them. And the perpendicular part has to have a right angle. So if you have those things, now I know the blue segments are the bisectors, right? The blue segments are my perpendicular bisectors. So P, D, P, E, and PF are the perpendicular bisectors. They all meet at one point, right? What's the point of concurrency? P is the point of concurrency. And from that point to each vertex, which is now the red lines, are congruent. So based on all that, I know that PB equals PC equals PA. So that's the concurrency of the perpendicular bisectors of a triangle theorem. All right, that point of concurrency has a name. It's called the circumcenter. So the circumcenter is where the three perpendicular bisectors of a triangle meet. In an acute triangle, they meet inside the triangle. In a right triangle, they meet on the triangle. This point here. In an obtuse triangle, they actually meet outside the triangle. So in, on, out. Acute is in, right is on, obtuse is out. All right, so this says BD is the perpendicular bisector of AC, find AD. So BD, which is here, perpendicular bisector of CA or AC. It means that this is a right angle. It means that this is congruent to this. And because D lies on that perpendicular bisector, what's the relationship between DC and DA? They're congruent. So I would say 3x plus 14 equals 5x. Subtract the 3x. Good. And it asks for AD, right? So take this. So just be careful because sometimes they'll throw on something that says like this length is 15, something to throw you completely off, right? The relationship is between the two segments that connect the point on the perpendicular bisector to the end points of that initial segment. Okay, this one says in the diagram, WX, line WX, is the perpendicular bisector of YZ. What segment lengths in the diagram are equal?
YV and Z equal V.
YV would equal VZ. What else?
YX is equal to XZ.
YX is equal to XZ. Good. And? YW equals WZ. And B says, is V on YX?
Yes.
Yes, and how do you know that?
Because of the converse of the perpendicular bisector theorem.
Good. Okay, and if you don't remember the name, it's because V is equidistant from the endpoints. Of YZ. Questions on that one?